Okay, so the recording has started. Theo, you can start.
Okay, so today I'm planning to walk you through the semantic class. And we are gonna go through the design documentation. And then if we have time, I can show you the latest evaluation results. The motivation behind the semantic class is that sometimes the jobs that the query that the user submit in compute engine, they are very similar. They exhibit a similar pattern, and we can learn some things from the execution of previous queries, and then we can apply them to optimize the execution of the next query. So this is pretty much the idea for every class implementation. What is different with the semantic class is that semantic class has the ability to understand the semantics of the contents, and it can be used between different users without them explicitly knowing what is inside the class. So that's the whole idea. So we will start by giving some examples, some motivation examples. We will see some competitive technologies, and then I will walk you through all the implementation stuff that we have done up to now. So typically we are working in big data scenarios, and we distribute compute engines. And the main framework, the main data structure that these compute engines use is a DAG, is a directed acyclic graph to submit. The users use that to submit jobs to the compute engines. Now this can be masked by other interfaces, but it typically boils down to a directed acyclic graph interface. So this is a typical example. The user wants to load a file that contains tabular data. Then it wants to filter the data according to a filter predicate. And then it can ask for a count. And also it can ask for a transformation and then a store back to the distributed storage where it loaded the data from. So this is a directed acyclic graph. The user will submit that. Typically, a driver responsible for executing this program will take over, and it will split this into multiple jobs. In this case, most likely the count job and the store job that you see in the boxes here in the regular boxes. And then it will further split these jobs into tasks, and it will distribute the work. Each one of the workers is going to do individually its own tasks. And then the driver is going to be responsible for doing the scheduling, the cooperation, and the execution of the whole program. And then when the driver finishes, it's going to return back the result to the user. Or in case of the store, it will return a verification that the job was successful. Any questions so far about the model of what a compute engine is? Okay. So what is the main issue? As we said before, right? So let's assume that we have like a filter here. We load some CSV files, and we try to filter them, and we want the temperature to be greater or equal than 100 Fahrenheit for all the records that we filter in, and then we do a transformation and so on, right? So Notice here that although we are working on a potentially small number of records, because we will only filter in the records that are in warm climate, during warm periods, and so on and so forth. The problem here is that we load the whole data set. So even if the records that are filtering is like 1% of the initial data or even less, we will still load the whole data set to the compute engine, and we will perform all the ensuing operations after that. So that's the approach that many distributed compute engines take, including Spark. So this is that's gonna happen there, and this of course has a lot of disadvantages. Mainly the storage IO overhead. You load the whole data set from the storage. You have to transfer if the storage and the compute clusters are not in the same data center or even in the same rack. You will have some network overhead to transfer them between storage and the compute cluster, which are going to be analogous to the size of the original data set. And also you are using a lot of computation and memory resources in the compute cluster that are analogous to the initial size. And this generally leads also to larger execution times as well, for all the reasons we mentioned above. Any questions so far? So what they do in the literature, they usually sacrifice some additional memory to cache content, and this can be like memory, like DRAM, or disk, like hard disk or SSD, or anything like that. And they use these cast results to improve the efficiency, the execution of future queries. So the cache itself does not need to be replicated or persisted for fault tolerance, because the contents are not so important for correctness. If you do not find something in the cache, typically the compute engines can easily revert to the baseline plan, and they will execute the initial plan, which means load from the source data and execute the plan as follows. So let's see some example of what we can store in the cache, right? What type of content we can store in a cache in order to improve the execution of the future plans. So let's take an example. Let's assume again the previous example. We have some, here you can see the physical plan as well. So we have some partitions. Let's assume that the red data are the hot temperatures, the yellow data are the warm temperatures, green data is like warm, cool, and blue is like cold. We are going from hot to cold here with color coding. And then you have a filter operation here and a transformation, and then some further operations. And you have 4 partitions in this particular example. So in case of the baseline execution where you don't have anything cast, this is going to proceed as follows. You will run 4 tasks, and each one of them will handle a single partition from the initial distributed storage. Now, a thing you can do here, if we assume that the filter is is done on top of the temperature attribute, and we have the previous filter that it filters in the hot temperatures, let's say, we can use repartitioning. So in this case, let's assume that we have already done a repartition of the data in terms of temperature. And we have stored the contents in the cache. You see here in the red circle. So again, here, like what we do is like we make again 4 partitions, but now we sort the whole data set according to temperature. So the first partition has all the hot records, the second has all the warm, and so on and so forth. So now when the same query comes that filters in the red values, essentially the hot records, the records with hot temperature, we can load from the disk only the first partition because we know that the other partitions do not contain any hot records. And this is a very well-known technique. It's called partition pruning in literature. And now you have all the benefits that we discussed. You load only 1/4 of your initial data. You transfer only 1/4 of the initial data through the network, and your compute cluster only allocates resources for 1/4 of the data. So it's a win-win situation. You see here, we run only 1 task as opposed to 4. The problem with that is that the initial part requires like shuffling of the initial data set, and the initial data set is pretty huge. So this will lead to a lot of overhead just to do the repartition. So in order to take, yes?
So I think a underlying assumption here is that we need some additional data structure to indicate, how this repartitioned content is organized, right? What's the attribute range for each partition?
Yes.
So how would that be organized? How does the Spark know there's such a additional metadata for you to find out about that information?
Good observation. So you indeed need something like that. Fortunately for us, we do not have to implement it ourselves. There are formats that keep these formats that you can store the data that keep this kind of information. And one format like that is like Parquet. So Parquet will store this type of information by default.
Okay.
So
yeah.
This is Hong. I have a question. So when you talk about the baseline, right? Execution. So in the baseline execution, how do you how does the cluster partition the data? I mean, based on what? Does it has the metadata information to partition it, or any specific ways?
Yes, so that's a good question. So first of all, because the initial data is like source data, we do not have any control of it, right? So we do not control the partitioning scheme or how the data is stored in what format and so on and so forth. This is up to the application user, to the Spark user, for example, right? So in this example, because I had a particular data set in mind when I made this example, the data is partitioned in terms of time.
Okay.
And like a secondary, but also region, right? But this is like a secondary attribute in partitioning. So what you see in partitions is, for example, the first partition would be like January from specific regions in the map, right? And then it will be January from some other regions, and then you will go to February and so on and so forth. For my example, I assume that the initial partition is completely random. So it's like almost, it follows the uniform distribution, right? The values and so on.
So you're saying, so when they do the baseline partition, the cluster actually has no information of any sort of metadata of the source data. Or it does.
It might have, it depends on what format the user has chosen to store the source data. Now there is a trade-off, right? So for example, I mentioned Parquet and CSV are the main format that we have worked with so far. But they have advantages and disadvantages. For example, when you write the data, right? When you want to integrate like new data and so on and so forth, Parquet is not an easy format to work with. CSV is very easy. You just add some lines, right?
Right. Yeah.
But when you read the data, of course, Parquet is much better compared to CSV. So
rich metadata.
there is a trade-off. Source data has this issue because source data typically, like especially in this example, which is IoT, you get the data from sensors, right? And you have a continuous flow of data coming in your cluster, right? So using like Parquet is probably not to store it. It's not very very good, at least from the beginning. Maybe then you can pre-process, like you can do like a pre-processing step, and but this will be like repartitioning essentially, and transform into Parquet format.
So then your method one, so then to sort and repartition data. So that also has a limitation, right? So that depends on what metadata do you have for the source data. Otherwise, I mean, if it's a CSV, you don't have any sort of metadata of the file. How do you resort the source data? Otherwise, it will be too expensive, right?
Yes, it is. It is typically very expensive.
So and also I'm saying it has a limitation for the different format, right? For the CSV, yes. I don't think you can do it.
Yes, so CSV is gonna be like more expensive, right? If you store it in like Parquet, for example, the source data is in Parquet, it's gonna be cheaper. So that's correct. But you can always like it depends on how many jobs, right, are gonna benefit from this repartition going forward. If the number of jobs that benefit is like 2 or 3, then typically it doesn't work to do the repartition because the cost overcomes it is greater than the benefit, let's say. But if you have like 100 jobs that benefit from this specific repartitioning, then typically it worth the trouble. So the benefits outweigh the costs in this case, right? So you are right. Repartitioning cost might vary, but also like you might have benefits even if it is very, very expensive. It depends on what is the type of jobs that you're running on top of it.
Right, and another point is that in the most general cases, even though that's not how we implemented this, repartitioning can be done offline, right? Not inline as the query processing.
Yeah, but in that case, you don't even know how do you want to repartition it, right?
Yeah,
so you most likely want to index it. You mostly want to index it, then cache the
yes.
then maintain an index, right?
This is correct, but we try to predict what are going to be the future jobs based on the history, right? And if we see that, for example, there are a lot of jobs that use a filter on the temperature attribute, then we might take a decision to repartition on the temperature attribute. So that's the way we do it. Now, it might be beneficial, it might not. It's a risk that we are willing to take. We have
Okay.
some results, so you will see later how repartitioning affects the execution time and all of it.
Just a quick note, the other technique that people are using are they're creating indexing for those data that, you know, not like columnar or like a Parquet, right? There's index embedded. So they have an external index. So that's pretty common in the data warehouse, the data lake, those kind of architectures.
Yes.
And then,
I will go
right, you have to go to
indexing.
the detour, right, from Spark to that index database and then to filter out data that way. Right? So if you do that way, partition still matters, but you know, at least you have more information, right? The index you can create much more than Parquet can create, right? So that's another right twist, I guess, on this one.
Okay. So another technique, as Young mentioned, is indexing, and we use a particular one which is called data skipping or file skipping in our case. But what we do in terms of that is for each partition in the above example, we will keep some information about some metadata about the data that is stored here. So typical examples are min-max values for each partition of a numeric attribute. In case we have a category attribute, and keep a list with all the values. So for example, if we have a classification attribute, like here in temperature, instead of temperature, we could add like hot, warm, cool, or cold, like red, yellow, green, or blue, like you said. And we can keep a list like which says like which of these values do you have inside each partition, for each partition. And then there are also Bloom filters. They're like more sophisticated ways to keep metadata that is also efficient in terms of that they don't take a lot of space for attributes inside the single partition as well. So an example here, if we have a slightly different distribution in our initial partitions, and here you can see that the first partition has very warm values, so it's probably like summer or something like that. The second partition has 3, the third partition has 2 values, and the fourth partition has 2. We can keep this indexing information for each partition. And then when the filter comes that we want the red values, we can say, oh, P3 and P4 do not have any red values, so we can safely eliminate them. We can do partition pruning and we can eliminate them from loading, similar to what we did in repartitioning. And then we only schedule the P1 and P2 partitions for execution. So this is much cheaper compared to repartitioning because we keep only the indexing and it's a single pass on the initial source data to keep that. Keep in mind that it depends on the format, but the source data might already have a similar type of information embedded to it. I mentioned Parquet before. So Parquet kind of keeps that information embedded inside it. But there are a lot of formats that do not have this information, like CSV. And so now we can, as I said before, we can safely eliminate these two. The issue with this technique is, as I said before, it's very cheap. It's very nice. It does not occupy a lot of space in the cache because you just keep some very simple metadata. The problem is that it's not as applicable as repartitioning. So here you see that we had a very nice distribution that worked for this technique. But if we have the above distribution, this technique is not going to work at all because all 4 partitions have all 4 attributes, attribute values. So here you are not going to eliminate anything with file skipping, with data skipping index. In this scenario, with this distribution. That's the negative effect of this technique. Any questions about data skipping before I move on? Okay. The third technique and the last that I will go through today is intermediate data caching. So what you can do in this case is like if you had the previous query that had a filter on the red values, you can store the intermediate data that arises after the filter operation in your cache. And then if an ensuing job comes in that uses the same filter, instead of loading from the initial data set and executing the filter, you can load from the cache, the intermediate data, and also eliminate the filter operation as well if you can, and continue with the next operations. And this technique is it's the best in terms of efficiency when you use it, when it is utilized, because not only you are skipping like you do much less data load, but you might skip operations. So you might get away with less compute cycles as well, compared to the other technique. The issue with this technique is that it's not as applicable as the other ones. Notice here that the next jobs that come in should have a filter in for the red values. So this is the only way this is applicable again. While the other two, even if it was like yellow values, if the filter was like for yellow values or for blue values, would still work. So this is like more narrow. The usage is like more narrow compared to the other technique. It is not utilized as much.
So Theo, just want to confirm something. So for the repartitioning scheme, do you always store the repartition data in Parquet format, regardless the format of the source content?
In our current implementation, we store the intermediate data and the repartition data in Parquet format.
Regardless of the format of the source?
Yes, because we control that.
Yeah, that's fine. I'm just trying to confirm. Okay.
Yes. So I after a short research that I did, I identified Parquet as the best format to store the data, and I use Parquet.
Okay.
And for metadata, because it's it is very small in terms of size, I use JSON. So I use a convenient format that can be parsed quickly. I don't care so much about the efficiency there, because
I'm sorry, what did you say you use for metadata?
JSON format.
JSON. Okay. Another question is for what do you call that? For intermediate results, right? In principle, you can store them in memory as well. Do you think Parquet is also the right format for in-memory storage?
Like the memory that we plan to use is Alluxion, the memory cache.
Right.
So there the caveat, if you want, is that Alluxio should have a backup in the disk as well.
Okay.
So there you don't have a choice. You have to use a storage format too. But in an ideal world, you could get away with using other types of format. So,
okay. So as we integrate with Alluxio, you still plan to use the Parquet format for memory?
Yes.
Okay.
Because Alluxio needs to be backed up by by disk distributed storage, and usually it's HDFS. So you need to use a format that is good for storage as well.
Right, but I might be getting ahead of you. So does that mean you also compress the data in memory?
Yes.
Okay, so is it possible to store the content, intermediate content, in uncompressed Parquet, but then when you back it out, you compress it? Is that possible? I'm just worried about the decompression overhead here.
Yes. So Spark offers all these choices to the users when they store data manually in the Spark cache. In the memory, they can store it either compressed or uncompressed. They call it serialized, but it's essentially very similar with what you propose. But you might see benefits. Yes, the answer is yes, but it will make the implementation much more complex.
Okay.
At least as it is right now. If we can find something clever, then it might be simple. But with my current plan, this will take like quite a lot of effort.
An alternative is to assume that intermediate content will not be that big, so we always store them uncompressed.
For metadata, I guess you can assume that. For the caching, not so much. Caching might be like gigabytes in a large data set, right? So to give you an idea, Parquet is very aggressive compression. It uses very aggressive compression, right? So something uncompressed might be like 30 gigabytes, right? And with Parquet, it might come down to 8 gigabytes.
Okay.
So there is a huge difference in the cached content if you store 30 gigabytes and if you store 8 gigabytes, even in memory, right? It might be more inefficient when you load it because the load from memory is fast. So it's not so important to load less data. And you don't have to decompress it. So it's going to probably be faster, right? But it's going to occupy more space in your cache.
Yeah,
which is the downside.
That makes sense, right? Another way to look at this is that since the cache is most for intermediate content I'm talking about, right? It's most likely reside on the compute side, and then we should have enough compute power on the compute side to do the decompression.
Yeah.
Okay.
We have memory cache in the storage too. We assume that you can have, but yeah, you're right on that. But it's just a matter of it's a trade-off there. You lose space, but you gain a little bit efficiency. So it's a good question to look at it.
Okay.
Okay. So for the semantic cache, we will focus on all these three different types of content. We are actually the first cache that can store these three types of content. And also know semantically what they mean. We would like to provide shared read access to the content. So that means that multiple users can benefit from the cache and from each other execution, job executions. And as I said before, semantic aware capabilities. So the users themselves do not have to know what the contents are for. So you see a file in the semantic cache, which is called like repartitioning 0.2. You don't know what it is. This is fine. You can still run your query. You can still use this content with for your job. And you might not know exactly what this is about, and you will get the correct result like automatically. So that's what we mean by semantic aware capabilities. And these three together have not been done by other technologies. And let me talk briefly about two other options that I have seen being used as a CAS. The first one is the native Spark CAS. The problem with this CAS is that mainly is that it is not shared, and users typically can CAS only intermediate data there, mostly. So when a gray user here passes a result, the gray user has to do it manually, first of all. It goes to the distributed compute engine, and then this one uses like the plan for this filter along with the data, and it caches it in a distributed multi-tier cache. Can be memory or disk. That's why I call it multi-tier. The problem is now a third user comes, it executes a similar filter operation and then an ensuing operation. It goes to the distributed compute engine. Because the cache is not shared, there is no way it can access this, the cache of the gray user. So here the load is still gonna be inefficient. It's not gonna be able to load from this result. Aluxio offers a solution for the shared cache. The Aluxio has a different kind of issue, and it has to do with the semantics of the cache content. So here again, the user can say, I want to store the results of this filter operation in a file called rfilter.dat in Aluxio, and it will go down to the shared cache that Aluxio uses. Again, it's multi-tiered. It's mostly memory, but it can have like a backup disk as well. So the gray user stores this in rfilter.dat. Another user comes in, he tries to execute again the same thing, and it cannot use this content again. The reason is because it doesn't know what rfilter.dat contains. And even if the yellow user knew, it would have to do that manually in his job, in his or her job. It would have to insert the load manually to the job that it does. So there are two problems here. The first one is that there needs to be a third channel that communicates to the yellow user what rfilter.dat contains in terms of semantics. What is this content? And then the yellow user, the second problem is that the yellow user would have to understand what the content here to optimize its own job and manually change its job to use the rfilter.dat to take advantage of it. Any questions? Okay. So this is the problem that we were trying to solve essentially, right? So we want shared content so on to automatically get the results from the cache, even if you don't know the contents of the cache, what they do. So we implemented semantic cache. We would like to support 4 different modules, 4 different modes. The first mode, 3 different modes. Essentially, the 0 mode is the default. The default mode is that all the things are super manual. The users have to do everything. You have a cache administrator that is responsible for maintaining the contents in the cache, and the users can manually ask for the cache content. This is the most that Aluxio would actually provide. We can use this mode, but semantic cache is not useful in this mode, essentially. The first mode, which we implemented like 3 months ago, more or less, it provides like manual cache management, which means that you should have someone who is responsible for maintaining the cache content, and we have an API for that, to add content to the cache, to delete content, to configure the size of the cache, and so on and so forth. But the main difference, which is a huge difference, is that the user's queries are automatically optimized according to the semantic cache content. So now the users do not have to do any manual transformation in their jobs in order to get advantage of the cache content themselves, like they have to do in Alluxio. Okay. And I'm going to jump to option 3 directly. Option 3 is the fully automatic mode. Now, not only do we handle reads from the cache automatically, but we also eliminate the need from a cache administrator. So what we do is we fully control the cache management based on an optimizer, a planner, essentially. This one, it can be customized, so we can provide for a way for users to provide their own policy or their own optimizer if you want. And that would mean that essentially they would have like something like an eviction policy, which is actually mode option 2, mode 2. And we have already implementation for mode 3 in place. We are still making it better as we speak. Jit and Ning Chao have built like some new models, and we are slowly integrating them in our baseline approach for mode 3. But we already have something complete there. We are just making it better.
Can you stay there for 1 second? Just go
Yes.
back a little bit. So I'm trying to understand. Give me 1 second. Let me just read your text quickly. So I see. So I'm trying to understand the difference between option 1 and 2. So in option 1, the cache administrator, the human, will have to make all the decisions, while in
Yes.
option 2, the human is given some recommendations, right? And then they can choose. So that's the main difference.
You can see it as a hint, the option 2, right? It gives us like a eviction policy or the strategy that we want for evictions and for the additions, right? And then we use that.
So
but
so
it's
you
automatic.
understand. So for option 2, the queries are also set. No, who handles the query? The query is also has to be adjusted manually, or it was
No. The queries from option 1 up to option 3 are optimized automatically. The read from the cache is always optimized.
What about option 2? How is the
option 2? Option 2 handles the writes a little bit better, and the evictions, right? The deletions from the cache. So when you want to put a new content on the cache or delete new content, this will be done automatically, but we still want a hint from the user to give us like a score or an eviction policy or something of this.
Right. I'm asking, that I understand. I'm asking about how the user queries are satisfied. With option 1, you said the user queries are automatically adjusted based on semantic cache. How do we handle that for option 2 for user queries?
The same thing. So you see what, like automatically, you see what are the contents in the cache, and then you optimize the query according to the content. It's the same for option 3 too.
So maybe
this is the same technology.
Maybe we can add that line for option 2, because we don't have that statement for option 2.
Yeah.
Okay. So
in that, right?
yeah. So you are saying we have implemented option 1. We have implemented option 1, right? And then
yeah, and it is fairly robust, I believe. It works very well as far as I can tell.
okay.
And option 3, we have a baseline implementation.
Mm-hmm.
It is not bug-free by any means. We still find bugs, like in great frequency. And we are also making it better as we speak, because we are building new modules that are better from the previous ones.
Right. So the question is, if we already have option 3, why should we bother with option 2?
In case a user wants to have a better interface for implementing its own policy, now only a developer can do that. So essentially, we do not provide interface for that. The developer would have to implement its own planner, essentially, to get its own policy. I was thinking of something simpler than that, where we can have like a function with a score or something like that the users can define. And then we can take that and we can have a custom planner that will use this score and make decisions according to the user input. But it's not mandatory. We can skip this step if you believe that it's not important. It's just like a nice intermediate way to provide all levels of involvement from the user, right? To break it down a little bit. But we can remove it.
So right now, do we have that as a backlog item?
No.
No, right? Okay, that's fine. I'm just curious about the status. That's fine.
No, but it shouldn't be very hard.
Okay.
We tried to find also with JIT, because he has implemented 2 more optimizers, 2 more planners, essentially. So now we have like 3 planners. They are not well tested, but we have the code. We can identify some common things between them, right? And then it will be easier to make the custom planner work, because we will see what's the difference between them, and we can say, oh, this is probably something that we need to ask the user for. So that's why we went to mode 3 directly, to kind of a little bit experiment in order to see how the user can define the policy here. Okay. What is the right interface?
Right. Just a cosmetic comment. Every time you guys say a cache planner, I have to think, is that a cache placement a planner or a query planner? I think you mean the former, right? It's about what to
cache placement, yeah.
Right. So maybe we should, okay, because you actually know in query execution you also have a planner. So
yeah.
So but you're referring to
so we call the first planner and the second optimizer essentially in our implementation. Now that the design document basically here has to put planner. So this is our difference in our implementation. Planner, I think of it like that it handles the rights and it looks more to the future. It needs to have some future plans in order to take decisions. Optimizer is the per query optimization that we do.
Okay.
Okay. So semantic as contents in principle can be anything useful that might decrease the query's execution time, utilize less resources to execute queries, minimize the communication, and also decrease the cost of the whole platform. And as of now, the R context is partitioning of source data, files keeping indices of source data, and cast intermediate data. And here is the architecture that we have. The compute engine is depicted with red. The parts that involve the cache are depicted with green, and the storage, the source storage, is depicted with the blue color. Now, what we do, I'm gonna go through all of them. The compute engine driver is basically a centralized node in the compute engine that is fully responsible for executing the user's program by using the resources, mainly the workers. The workers are very simple processes that are responsible for executing small portions of a job called tasks. And their number can scale up and down according to the job needs. Semantic Cache Client is a module that we implement. It's a plugin in the driver, essentially, that will help us communicate with the Semantic Cache Manager, which is the Semantic Cache service that we have built. And the Semantic Cache Manager is a centralized service that maintains semantic information and also the size of the cache content. And we use a baseline cache storage. Some typical examples are storages, for example, that expose HDFS API. Right now, we support only HDFS, but we plan to support Alluxio as well in the future. And we use 4 different tiers. We assume that the cache, this baseline cache, can be like either at the compute site in memory. Alluxio can play this part. In the compute site at disk, the backup option for Alluxio can be this part. Storage memory, now for this, there are not a lot of technologies that I'm aware of, but I'm pretty sure many storages have a memory cache. And storage disk, which can be like an HDFS on the disk side. You can also use the same storage as the source data. You can give some to the cache, essentially.
So I have 2 questions here. One is, I know our current implementation only supports disk cache. Is it this on the compute side or storage side right now?
You can also put HDFS on the compute side, but most implementations it would be on the storage side. Right now, our storage in the compute cluster are in the same physical nodes.
Okay.
So it's not a big difference.
Okay, but in a disaggregated, in a true disaggregated architecture, what do you think the
storage disk? So this would be like it can be like an extension to the source storage, right? That you use as a cache.
Okay.
You can see it like that.
But let me see. So why not using the compute disk? Because we assume that there may not be enough capacity on the compute side.
The compute nodes, right? The compute servers would also have some disk resources. There is no way that they have 0 disk. So you can utilize them as a cache too. But we do not use them because, for example, you can use them with Alluxio, for example, as a backup for the Alluxio. You can use HDFS there too. But you are not going to have as much disk as you have in the storage side.
Right. Well, I understand what you said. What I'm getting at is that instead of saying we have 4 options here, as you list here, can we just say let's focus on 2 options? One is the compute memory cache, right, with a possible backup on compute disk, and then the other one is the storage disk. And then we don't need to worry about the other 2 options.
Yeah. I'm telling like which ones are supported. It doesn't mean that I use all of them. I actually use only.
I'm just saying going forward, right? What makes sense?
Yeah.
Even as we present our design, I think those 2 tiers probably are sufficient.
Okay. So the middle tiers can put them as option. Yeah. And then the source storage is where the source data lies. And the Semantic as manager has no access to it. In particular, yeah.
I have a question. So in this figure, right, use this chart, from the driver, the source manager, semantic client has a dash line to the cache storage. What is this for? I mean.
Yeah. So the driver sometimes queries the storage about metadata.
Yeah.
What is the size of the file, or it might communicate with the storage in order to find other information if the file is still there, and so
information
on, so forth.
I mean, shouldn't this information goes to the cache manager? I mean, so the cache manager doesn't talk to the cache storage, or that doesn't query the storage at all?
At all.
Instead,
no.
it's a client.
It's a driver. Yeah. It might be the client through the driver. Yeah, but mainly the semantic as manager does not need to communicate at all with the cache storage or the source storage as of now.
So another thing is I think on the semantic cache manager side, it has to maintain an index, or or a database or some sort like that, just to understand the semantic meaning, right?
Yes, it has to. All this is in memory, but we have a plan to log it. I will go through it later. But it does have that.
Okay.
Yeah.
Okay. So another separate question is so looks like because I didn't say the detailed implementation. So the client just inform the workers where to get the cache data, right? So then the worker has to get the cache data by itself. So
yes,
in this implementation, do you need any modification on the worker side just to get the cache data?
No. So the worker can already communicate with the cache storage. This is an assumption that we make, right? So the worker should have access to the cache storage. Where we infiltrate is during the planning stage in the driver. So when the driver tries to do a job processing and tries to understand what the job is about, and tries to optimize the job before it gives it to workers, right? This is just a pre-processing step.
So you're saying this information from driver to worker is before it's running, right? So it has to plan all those informations.
Yes. So we infiltrate at this point, and for example, if the job is like load data from storage 1, right? We can change that in the plan and say instead load from cache storage 1. And then the driver will disseminate this information to the workers, and the workers are very dummy. They just execute what the driver tells them to do. So they will take data from cache storage 1 and they will work from there, whatever is the remainder of the plan. So, yes.
So in this case, right? So in this case, would it be possible that the whole cache storage is actually external caching, like a caching server, for example, Memcached or Redis or some sort of like that? I mean,
yes.
So is that possible?
Yes, as long as the worker like has a client for these services, it can be anything that you want. But right now we support only, as I mentioned before, right now we support only HDFS, and in the intermediate future we plan only to support storages that have HDFS API. like Aluxio is a good example. So I'm not sure if Redis and Memcache have HDFS API, but it's a requirement that the worker needs to have the corresponding client to talk to this storage, right? It needs to fetch the data. So that's the requirement that we have there.
Okay. Thank you.
So you said the metadata is in memory. So what if there's a crash of the cache manager? How are we going to recover?
So a crash in the cache manager is not critical in terms of correctness. It just means that you will have lost all the cache content that you had in your cache so far. So it's a matter of effectiveness. But there are ways to recover. I'm going to talk about it right now. But I'm going to talk in the next actually session, which is called assumptions. But basically, you can replicate to answer very quickly, or you can keep a persistent log. These are the two options that you can have in the semantic cache manager. But the semantic cache manager is not critical for the correctness. So this pipeline should work even the semantic cache manager is failed. It will just go to the source storage always. It will not go to the cache storage. Okay. So some assumptions that we have and we are going to eliminate most of them later on, if not all of them. The network between the semantic cache client and the manager must be reliable. We achieve that by using gRPC. This means that the messages are not corrupted, partially delivered, or delivered multiple times. Essentially, a message is either delivered once or it fails. So we get that guarantee from gRPC implementation. The driver does not fail during the execution of a job. If the driver fails, the driver is a centralized component, right? So the job is that the job will fail as well. That's not the issue. The issue is with the driver failing is that you might have an inconsistent state while the driver fails in the semantic cache manager. So for now, let's assume that the driver does not fail, and we'll see later how we handle the situation. The source data stored in the source storage is immutable, is not modified. We also deal with this, but for now, let's assume that your data is like static. It is what it is, right, and does not change. And the cache content in cache storage is always available and cannot be corrupted or modified without a semantic cache manager approving the modification. So this is also a strong assumption. Someone like this node, this storage part might fail completely, or it might be corrupted or something like that. So we will see how we deal with that. As I said before, let's assume for now that the semantic cache manager, although it is centralized service, is always available and cannot fail. And also, the last assumption is that access control works ideally, meaning that the user that has access to the cache content, if and only if the user also has access to all the source files from which the cache content derived from. So this is a security kind of assumption, right? And as I said before, all these assumptions are going to be lifted or weakened to more realistic assumptions by things that I'm going to introduce later on.
Do you think we should add another assumption, which is that the cached content is validated periodically, right? You know what I'm talking about? When the source database is changed or modified, how do we make sure that the cache content is still up to date? So that
this is this assumption. So I will tell you how I deal with this later. Yeah.
Okay.
Semantic cache manager. I will go directly to the figure. So you need to tell to the semantic cache manager what are the what are the tiers that you are using. What is the essentially the storage URI for each one of them. As I said before, we support HDFS, so this would be like the HDFS name node address, essentially, for each tier, and then what is the available size. And all these are given through a semantic cache configuration file to the semantic cache manager, and when it is initiated, it initiates with empty sizes for each of the tiers that are defined here. And I use the tiers that Dr. Lei suggested that we should keep. Semantic cache client, it should be initiated inside the application user code. We will see more details like how we do it in Spark later on. But essentially, it's one line inside the user's program to activate the semantic cache. So how do we do the semantic cache write? So we provide 3 different APIs. The first is repartition. The user has to specify the source and the attribute on which the single attribute that it wants the repartition to be on. Then the data skipping indexing is the same thing. And we have the intermediate data caching where you give the plan to cache this also. So the idea is that the cache admin will have a client API, and this will give him the ability to interact with the semantic cache manager. It will write, it will use one of these 3 commands. It will write a candidate, and then it will define a candidate is one of these 3, right? It will define a name for the candidate, and then the tier for which it wants the data to be stored. The semantic cache client then will take that and will try to make a reservation on the semantic cache manager. It will use also a module. Will use the help of the driver to find out what this content write size is going to be, right? The estimated size. And it's very important for correctness for the estimated size to be an overestimation of the actual size. So if it is an underestimation and you reserve less size, this might fail. If you reserve less size than you actually need. So it's important for this to be an overestimation. So semantic cache manager will determine if they can do this reservation according to size, to the size capacity, and it will determine if it has like this content already. If this content is stored, then it doesn't need to do anything. It will just return, I have already stored this content, and so on and so forth. And then the semantic cache client, once it gets the answer, it will initiate the write to the cache. And if it's successful, it will go for a second round of communications with the semantic cache manager to confirm that the cache content is stored or not. And the notification would also include some feedback about the size that was occupied in the cache. So here, if you go back to the initial figure, what happens is initially you reserve some space in the semantic cache manager. It's like a 2-phase commit, actually. Then you get back a confirmation that indeed I have reserved this space for you. Then the semantic cache client through the driver actually adds the content to the cache. It gets back feedback about the real size that it occupied, and then through the driver again, and then it sends this information to the semantic cache manager, which fixes the actual size now in order to free the remainder of the space. And this is it. This is how we store content in the cache in mode 1. This whole thing summarizes the process. So you can see here the estimated size is a little bit more. But after we get feedback from the semantic cache client, we fix that. So this is the case where we have a successful write. That's what I described right now. Delete is pretty similar, only in the opposite way. You send a request to delete the that you use to cut it. The client propagates the request to semantic cache manager. If the content with this name is present, then you actually delete it. And you send a reply to the client. And the semantic cache client deletes the actual content and replies to the semantic cache admin. Any questions for that?
Yeah, how do you know, how do we guarantee that while a cache entry is being deleted, is not read at the same time by another application?
Oh, that's a very good point. We do not actually guarantee that for now. The idea is that, again, you might see, I might detail that later, but the actual implementation is also two-phase commit. So what happens in the real world, you delete it from the metadata, which means that the semantic cache manager is no longer able to use it for optimization purposes, this content. And then you look the semantic cache manager, I keep a number of references to this content. So if this content is referenced by other clients, then you do not actually delete it. And when the content is dereferenced by all the clients that are actually using it, meaning that all the clients that using this content have either stopped working, stopped working, or they have stopped like gracefully, then you can easily like delete this content as a semantic cache admin. It's gonna show up in the status as so there are actually 3 types of statuses that you can see when you ask this command. So the first one is what reservations you have made as a semantic cache admin. The second one is what are the actual active contents and which contents are marked for deletion but are not deleted yet from the cache.
So
and once it's safe, once it's safe to delete them, the semantic cache admin should be able to issue a new command to delete them.
do you think we can simply associate a read-write log with each cached entry?
We just took a number of references.
You're describing a read-write log, right? We don't have to implement that ourselves, right?
Yes, we do something simpler. We it's like a read-write log. Essentially, what we do is like I'm not keeping only the number of references. I'm also associating the references with the Spark client ID. right, that is using them. Actually, the implementation is like a read-write log, but it is not very useful to do it like that because the write is only once for its content, right? You only write in the beginning and then it's always reads. And then it's like when the Spark client that has done the read terminates, then you can easily delete the reference there. That's what we do.
Yeah, so that sounds good. So can you just add a couple of lines to document that thought, because I'm not sure will be.
I think I'm explaining later in one of the assumptions that I do, but if it's not good, I will document that here.
Okay.
Semantic as read is automatic, as I said before. So the way we do it is the user submits a job query to the driver. This is the interaction of the user, the normal interaction. The driver tries to optimize the plan, and we have injected the semantic as client optimization on it. And then the semantic as client transforms the plan from its initial compute engine representation to the native semantic as representation and sends the plan to the semantic as manager. And then the semantic as manager optimizes the transform plan according to the contents and marks any relevant contents as used by the specified session application. This is a reference that I was talking about, and sends the optimized plan back to the semantic as client. Semantic as manager then should not delete the specified contents until the session application is terminated. And then the semantic as client transforms back the plan to its initial representation and sends it back to driver, thus finishing the semantic as optimization step. And then the driver continues with the optimization and execution of the query and sends back the results to the user.
I'm sorry, you lost me a little bit. So in step 5, you said the semantic as client transforms back the plan to its initial representation. What does that mean? The initial representation?
We transform the plan once
from
the initial compute engine representation,
right?
The native semantic as representation.
Oh, I see. You okay? I see. You don't mean the tree is the same. You mean the representation format is the same, right?
Yes.
To the initial representation format, but the DAG is different now, right?
Yeah, I think I have some examples.
Right. Sure. Because when I see initial representation, I thought you're going back to the initial DAG, but that's not what you mean.
No.
Right. So
initial format. Maybe I should write initial.
I the format there. Right.
Okay. And here analyze a little bit with the step 4. How does the optimization happen, right? How do you optimize the plan according to the content? So you can find this in this figure in detail. So the basic idea is that you go through the plan from top to bottom. Top meaning the last operation, and bottom is the first operation. They're actually the load operations. So you look at the root and you say, do I have this content cast, intermediate data cast? If yes, then I replace the whole plan with a load from the cast. If I don't have this cast, then I go to the children of the root and I continue recursively. In the meantime, I record any filter and shuffle attributes that happen on the nodes. And this is how I look for intermediate data. If I reach the children, the bottom of the tree, without having found any intermediate data content, Then I look first for repartitions according to the filter attributes that are directly on top of the source nodes. If I find any repartition that can optimize the specific query, then I replace the source data with the repartition data load. And then I look for file skipping indexing at the end, same as the repartitions. And I do replace with a special node which is called load with indices, which means look at the file skipping data, and if you find that you should skip some partitions, then do the initial load with it without this partition, without this file. So these are overall for mode 1 so far. In mode 3, remember, we eliminate the admin. And what we do is like slightly different. So we also do the write ourselves. I'm gonna go directly to the diagram here.
Before we go to mode 3, do you have an example of your mode 1 query processing part, like how we transform one query to a cache-based plan? Do you have an example?
But let me see. I think you have asked for it before, and I have included one. But maybe I didn't do it in the shared version, and now I've lost it. But you want an example of transformation, right?
Right.
Yeah, I will include one. This is easy.
Okay.
So here it's slightly different. So what we do now is we inject in the same place as well our optimization rule, and we get a native plan from the compute engine. We transform that to a series plan, which is the semantic as format for the plans. And then instead of serializing this plan and sending it over to the semantic as manager, which was the previous step, we now do some additional steps. So first we select some, we send the series plan to a candidate selector. This candidate selector is responsible from finding out from this plan what we can write to the cache, what are potential write candidates for the cache for this plan. And I'm gonna explain a little bit later how this procedure works. And then we have some write candidates from the cache. And we use a size estimator afterwards to estimate some costs in terms of I/O for these candidates. So a typical example is if I have a repartitioning, for example, a size estimator would estimate the write cost for the repartitioning. So how much space the repartitioning is going to occupy in the storage if I plan to do it, to actually do it. And this is an estimation because if you don't do it, you never really know. And the second type that we have is like, for example, if we have a repartitioning on temperature and I have a specific filter on top of on a query on the temperature attribute, then how much data I will need to load from the repartition. So this is another size estimation aspect. And after you have like these numbers, you can you have some candidates with all the estimated costs in terms of bytes, and then you serialize them and you send them over to the semantic task manager for optimization. And then the semantic task manager deserializes them and along with the current contents that it maintains, current contents of the class. And also it uses a predictor, which is fed all the history all the historic information before. In this one, you can see only the current plan, but you can assume that this was done for the previous plans too. According to this plan and some information that maintains before about other plans, it makes a prediction about the future, what are going to be the future plans to come. And the planner takes all this in, and it tries to make an optimized series plan, which will utilize the current contents, but would also potentially write a candidate, at most one candidate per plan to the cast. And then once you have the optimized series plan, you serialize and you send it back, and you send it as a reply back to the client, and then the client follows the reverse transformation path that it followed before in mode 1 and continues the rest. Any questions for this plan?
Just give me 1 second. So what? I'm sorry. I probably got sidetracked a little bit. What's the difference between figure 13 and 14?
13 is the client, the protocol in the client side.
Okay, I see.
And the 14 is the protocol in the manager side.
So the 14 covers the case of both caching and query optimization?
The planner is the
just
essential
the planner.
module.
Because
Yeah.
I see, because you also have the word optimize here. So that optimize does not refer to query optimization. You're talking about plan optimization. That's why I was confused.
Yeah, the planner utilizes the previous. Let me see. This scheme for query optimization as well. So the planner does both, does the placement and the query optimization too.
Oh, the planner does both. I see.
Yeah. We can separate them, and we can have the planner do only the placement, and then just send it to the optimizer, and the optimizer can do the optimization. But essentially, it's the same thing. So I can do it like that if it's easier to explain. So the planner can spit out a plan which has the placement part, and then I can pass it through the optimization to be optimized.
So, okay.
But this part is done inside the planner now, so that's why I have it like that.
That is fine. I'm only trying to understand. So when you say optimized series plan, the green box at the bottom, do you mean a caching plan or query plan? That's why I always got confused. I don't know which one we're referring to.
It might potentially have both.
Really? Okay.
Yeah.
Okay. So yeah. So maybe.
So let me show you an example. So you can
just give me 1 second. I think what might help is we always talk about those two things explicitly. We call one a cache plan, one a query plan, and then if you refer to both, then just say both. Say cache plan and query plan. When you refer to one, just say one. Otherwise, it's kind of hard, at least for me, to figure out which one we're referring to.
Yeah. Let me see if I have a quick example here.
Because earlier you have this thing called series plan. I think that plan only includes the cache plan. It does not include the query plan, right? In yellow box.
Yeah.
Right.
Yeah, I will change that.
So
yes.
In figure 14, what does the contents do in the to the planner? So what does the planner use the content? So first of all, what's a content? How does it use
the contents are the existing contents in the cache, right?
you mean the cache index or whatever
content.
you cache this?
Yes,
right?
yes. So
Okay.
the planner needs them in order to first to optimize the current plan according to the contents, and also it plays a role in your decision, right? So perhaps if you try to cast the results of let's say you have a filter and then a projection, right? And you try to cast the results of the projection. You want to cast the results of the projection. If you do not have any other contents related to that, you might decide that this is beneficial and you might do it. But if you have already cast contents for the filter operation, which is the below operation, you might say, I'm not getting enough from writing the projection results to the cast. I have already the filter results. I can just do the projection and be done with it. So it plays a role also in your decision to write to the cast, but it's also very important for optimizing the queries.
Okay.
And, let me see if I can find an example, so you know what I'm talking. Let me see. It should be output series plan. Okay, here is a good example. So can you see this?
We're still seeing your design doc.
Okay, let me stop sharing and share the code. Can you see the terminal now?
Yeah.
So here is an example of the output that you will get, right? Here you have an aggregate operation, a projection, a filter, and then I have a series if node here. This is a special node. What this does, it says it orders it to do a series file skipping indexing. So it says try to do file skipping indexing with this source and this attribute, and put the results in that position, right? So if this is successful, that's why I call it series if. If this is the condition, if the write to the cast is successful, then I'm gonna perform a series load with indices. And if it is not successful, then I'm gonna perform this part.
Why wouldn't the skipping index be successful? What could be the reasons?
The reasons for the write to fail.
Okay.
It can be anything. Like it can be the case that the source data is not available anymore, right? Or it can be the case that you do not have any resources. It can fail for any number of reasons that you can imagine. It typically will not fail. Like in almost all of my runs, I have never seen it fail. So it doesn't fail a lot, but it can fail for external reasons.
Okay.
So this, in the condition statement, it has the placement query, the cast query, as you call it, right? And then the overall part is the optimization part, right? Here in the first condition, especially is optimization.
Hold on 1 second. So you first let me see. You first do a file skipping indexing, and then if it succeeds, you do series source load and load from the index, right?
Yeah, series
And
load with the index.
Right. If you
And you can see
fail,
here I'm reading the indexes, right? I have a filter operation and I have a projection, and this will essentially give me all the files from the source that I need to read. And I will use that to make this series load within this.
right.
Otherwise, if you cannot use that, you will load from the source. You will not load from the cache.
Okay. So let me think for a second. So slow with indexes, project the series. So I'm trying to understand just bear with me, the order when you have like series load with indexes, then you have project, you have filter, you have series cache load. What's the order? Is it top down or bottom up?
Yeah, it will start from here. So it will load the index file.
Okay, and then you filter. I see.
It will apply the condition of the filter, the min-max conditions that I have.
Okay.
And then it will do a projection on the first attribute, which is the file name. So here I'm gonna get all the file names that are relevant, essentially. And then series load with indices, it's gonna, let me see, it's gonna, instead of loading all these files here, the 254 files, it will load only the ones that came out of the projection.
Okay. All right. All right. Okay.
That's the idea. So that's the optimized query.
Yeah. So I think it would be very helpful if you create a easier to digest figure for the design document.
Example. Yeah.
Right.
Yeah.
Okay.
This is a valuation example, so it's pretty complex.
No,
as you see,
the example
has a
itself
lot of operation.
It's fine. It's just that if we tie that into a design document and then make it easier to read, it'll be better.
Okay. Yeah.
Okay.
Yeah, I understand your terminology now, so I can make it obvious. You are saying that this has no separation from the thing in mode 1. We should make it clear that this also has the cache query.
Yeah, because you remember earlier when I asked you about the planner, you said the planner was really about planning the cache, but obviously you're doing the query planning as well. So just be a little bit more consistent would be better.
Yeah.
Okay.
And now, in the remainder of the time, I'm going to explain how the different modules work. So, candidate selector basically has two main principles. It needs to propose candidates that are going to be used for optimizing the current plan. It cannot be something irrelevant to the current plan. That's the obvious one. And it should propose candidates that do not significantly increase the cost for the current plan. So we don't want to do a write in the cache if the cost is much more than executing the query with the existing content. Example would be like if we have this projection and a filter from a series, from a source load. And let's assume that it has various attributes here, including temperature and ID. The candidates can be to create file skipping indices, to cast the results of the filter, or to cast the results of the projection. Notice that we do not put the repartitioning of temperature inside the candidates because it violates the second principle. It adds an extra shuffle for writing to the cache actually. So we don't want to penalize this query a lot by writing the repartition to the cache.
So help me understand. In the initial plan, you have a tree, right? And then, later on, when you say candidates for plan, are we seeing 3 candidates here?
3, yes.
Oh, I see. So that they're not related. I see.
Yeah. So this is the first one.
Right.
This is the second one, and this is the third one.
The second one basically says I do this tree, and then I cache that. I create an entry as well.
Yes.
That's what you
exactly.
Do. Okay.
Yeah.
Okay.
And it is clear that all these candidates, if they were already in the cache, would optimize the current plan. So we maintain the first principle. So we can use this candidate to optimize this plan. We can use this one and this one as well. They would all optimize this plan if they were already in the cache. Okay. Size estimator, we need the size estimator basically to predict the right size of the candidates. We need that for to reserve the appropriate space in the cache, which is useful in all modes. As I said before, in mode 1, you need to overestimate, right, the reservation space. It's critical for the correctness. But in mode 3, we use it for other substantial reasons as well. We need to determine the correct tire to use. And this will be useful for future implementations of the planner. And we also need to approximate the cost for creating the candidate, which is useful for every planner. And we can use the size estimator to predict the read sizes if and when the candidates are utilized. So this is also useful for the planner. And as of now, we have a very basic size estimator, which is pretty much dummy. We just make sure that we overestimate the right size of candidates. And the rest is pretty much arbitrary numbers that are trending towards the correct direction, but in terms of accuracy, they are not very good. So we make sure that the size estimator that we use right now is correct, but it's very inefficient. It's very arbitrary and simple. Predictor, we have two types of predictor supported as of now. The first one is an oracle predictor, which is configured with all the plans that we plan to run in the future with the same sequence that they are executed. So this is like useful in two ways. First is useful for the evaluation to see if we have the best predictor possible. Can we squeeze some performance optimization? And the second is if there are scenarios that you have a batch of queries coming in and you actually know in what sequence they're going to be executed. So this might also be like a realistic kind of scenario when you know what's going to be executed in your cluster in the future. And we also have a more practical predictor, which can be used in all types of scenarios, which is the reverse order predictor. We simply reverse the past plans that the semantic cache manager has encountered and return them as future prediction. And all the predictors have a specific window size. So they have a concrete horizon in the future. They cannot predict more than a specific point. And the planner, right now we support only one planner, which is the storage IO planner. We simply see how much data we load and we write to the storage, and we try to minimize that. And the way we do it is from the candidates that we have from the current plan, we select the top candidate. I have the formula here, but essentially what I do is I compute what is the current IO that we will pay with existing contents. Then I estimate if I put this content in the cache, right, what's going to be the IO that I will have with this candidate. Maybe current and future would be better. Potential. So essentially, I calculate the difference and I find the savings that I will have in bytes by using this candidate. And I pick the candidate with the most savings per write size for the cache. So I think I have an example later on so you can understand it. And I add this candidate to the contents. And then I follow the eviction step, which is the second step. You evict the content until the contents can fit in the cache. If the contents can already fit in the cache, I skip the step. If they do not fit, I again find the loads in bytes with existing contents. And for each content, I let me put potential IO here as well. I calculate how much load I would have from the cache if I evict this content. And I again find the potential savings that I have for this content, and I pick the content with the least savings per write size to evict from the cache. And again, if the content happens to be the top candidate picked in the previous phase, then I do not change anything. I just say that I'm not going to write anything to the cache in this step, which is very common actually. And otherwise, I schedule the necessary addition, which is the top candidate that's selected in first phase, and any potential evictions that I had in the second phase. And then the third step is to optimize the plan like in mode 1 with the contents derived from the first two steps. So the first two steps are the cache placement essentially, and the third one is the optimization step. And here I have a detailed example. So if you have this plan and you have the repartitioning of temperature already inside your cache, and you have these three candidates again, they're the same candidates as before. And you have these future plans from your predictor, which are really similar if you look at them. You can calculate the benefits per byte in the cache for all the future plans. File skipping will not be useful because you already have repartitioning, which is superior content in terms of performance. So you will actually not use that at all, and it ends up having like negative effect if you cache it because you pay for creating the content. Caching of the filter is actually very good because you can use it in all three future plans. If I cache this, I can use it in this plan and also in this plan as well. I can use this on all of these three. So it's a good plan, and it actually yields a better score. So, and the other one again is used only in one case, so it ends up with a negative score. And so I will pick this as a top candidate. This one, I will include it in the contents. And now, if I want to evict, I go through this procedure again. Again, the caching now is the superior content because it is always used, while repartitioning is never used because I have the cached content there. So I decide to remove the repartitioning from the cache to evict.
If you don't mind, could you explain the cost function one more time?
It's pretty much the same for eviction and top candidates. So here is the cost. In IEO, I will have with the existing contents for the future plans.
Okay.
So in our case, because I only have the repartitioning here, the repartitioning is useful for all three plans, so it's gonna be used instead of this in all three of them because it's gonna optimize them. So the cost is like 3 times to read the repartitioning data. It's not exactly like that because it depends also on the filter operation, but for now let's assume it's the same. 3 times to read the zero content, which is
I'm sorry, before you get there, just one line before.
Yeah.
The cost future plan, comma 0. What does that mean? That means
it means the contents I have only the zero content, which is the repartitioning.
you have the candidate 0.
The content, it's content.
We currently have, right? We currently have.
Yeah,
right?
yeah.
Okay,
Yeah,
so future plan. Okay, and then minus future plans 0, 2. What does that mean?
Means what is the cost I will have if I have both the repartitioning and the casting candidate inside the cast.
2, catch candidate number 2.
Yeah.
Right. And
it's this one.
Right. And how do you come up with future plans? What's future plans?
The predictor comes up with them. It's either Oracle predictor, which I know beforehand what I'm going to execute.
Oh, I see.
Or the reverse order predictor.
With the right window size specification.
Yes.
I see. Okay. And then so you minus that, and then you minus the write cache cost.
For candidate 2. How much I will pay to write it to the cache.
Right. Okay. And then you divide it by W2. What's that?
It's the size that I estimate that this candidate is going to occupy in the cache.
Okay.
I want to find the benefit per byte, right? That's my my score.
I see. Benefit per byte. Okay, that makes a lot of sense. Okay.
And then I found that this one, for each byte I write, I save 3 bytes.
Mm-hmm.
So it's a good candidate. The other ones have negative number, which means that they not save. They are actually costful.
I see. Okay.
And so I decided to include that in the contents. And now, because I have 2 contents, I maybe I'm oversized, and if I have to evict, I do something similar here. But for existing contents, you do not have anymore the cost of writing to the cache, because this is already written in the cache.
Okay.
So here the formula is a little bit different for existing contents compared to candidates, but this one is still the same.
All right.
And so because caching now is going to be used for all 3 of them, when I have both of them, and not the repartitioning. The repartitioning is actually offers me 0 benefit. I get 0 benefit from it, because either if I have repartitioning or if I don't have it, it's the same thing. The optimization is going to do the same thing. It's going to load from the cast content, from the intermediate cast content. So this will go to 0. And I can evict the repartitioning. Okay. So this is our current planner. JIT has implemented 2 more. We will document them, perhaps using the same example might be good, but we'll document them and have them explained as well. Now, for the termination, I just notify the manager that I have terminated, and the semantic cache manager makes sure to remove any references that this client has made, and it cancels all the withstanding reservations that the client has made. And now for graceful, this is for graceful terminations. When we have terminations, we have implemented this. So I can remove that. When we do not have graceful terminations, I have implemented heartbeats. So if the manager does not receive a heartbeat within like 3 minutes from the client, then I'm gonna decide that the client is dead. And I'm gonna again do the same thing as in the graceful termination. So this eliminates the assumption number 2 that the driver cannot fail. We don't care now if the driver fails or not. And update invalidate cache mechanism. We weaken this assumption so that we remember the source data cannot modify it. To source data cannot be overwritten actually. So before we send the optimized website, the server should be able to find the files along with their boundaries. This will help us determine if the cast content is relevant or not. And if it's still relevant, then we can use it. If it is not relevant, that means that it has been invalidated, then it's not going to be used. And at some point, the eviction policy should remove it naturally from the cast, or the cast admin can remove it.
Has this been implemented?
Yes.
It has. Okay.
Let me need as of now. Do I have as of now? Here. Don't think so, right? Yeah. So this is also implemented. Backup plan. This is actually weekend's assumption number 4, which is about the corrupted or deleted content or modified content without the semantic as manager approving it. So in this case, we can have a backup plan issued by the semantic as manager when it optimizes a plan. And in case the file is corrupted or it has been deleted or it cannot find the exact content that it wants, it can revert back to the backup plan. And again, this might be like chain of plans. I think I have explained that before, which can also lead to a cache load, or like the backup plan can be also be a cache load with its own backup plan, or it can be a source load. In this case, we finish the chain. The bad thing about that is that if the failure comes from the source data load, then we will have to go through the chain, through the whole chain, in order to determine that, and potentially we'll have an overhead instead of directly running the original plan and determining it's a failure. But hopefully the chain is not going to be very long. In most cases, 1 or 2 backup plans. This is not implemented yet. That's correct. And now for the centralized service, we have the logging proposal. So what you can do is you can log every change that you make to disk. And if you do that, if it fails, then when you start it back up, you can read the load and get update. And you have like checkpoints, stuff like that, all of that. And so on and so forth. This is not implemented yet. Another way that is alternative is to replicate. So in case of a failure, you assume that you have enough replicas to continue for semantic as manager. And then I have some plans for security. The access control policy, I think we have addressed that. The first part is about capabilities. I'm not going to talk about that. But the second part, which is to ensure that access control policy for readers are like not violated. We can simply check when we are giving read content to the user. We can simply check if it has access to the source content to begin with before we do our optimization. And if it has access to the source contents in his query, then it should also have access to the cast contents that they are used to optimize the query. And yes, so far for clients, we have implemented the Spark client. And here I detail where exactly I'm doing the injection in the optimization process. and also what I run in order to activate the Semantic Task Manager. And that's pretty much it for the design. Do you want me to go through the evaluation too?
Probably not today. We can do that in a different opportunity.
Yeah.
So, do we have any other questions for Theo?
So I have put down two things. The first is the transformation example, and also the terminology for the planner, terminology between cache placement and query optimization.
Right. Yeah, and
Is there anything else?
Yeah, I assume when Jit and Ningxiao have completed their work, that will be incorporated into this document too, right?
Yes, but not for Q2, not for the current release, right?
Yeah.
Maybe later release, yes.
Yes. Okay. All right. So this is very helpful. At least I refresh a lot of my memory. So thanks, Steve.
Yeah.
All right.
Thank you, Sue.
So that's all for
Thank
today.
you.
Thanks, everyone. Bye.
Good.